Okay, perfect. So this is a question, and it's all in the wording. It says, what a value of a is the solution of sine of a is equal to root 3 over 2. We would probably give our answer in radians. So what'd you say? Yep, pi thirds. Was everybody able to do it? And then also, you're right, 2 pi thirds. So because this is what value of a is a solution, you could have put either, and they would have it in their system that you could put. If it says list all of the solutions, you would need to list them all from 0 to 2 pi. But if it says list a solution, either or will do. They'll have it in there that you can get it right for putting either or. So I'm just going to stick with that one. Both are, obviously. Okay, awesome. Okay, it says, what's the amplitude? Go. Problem number 2. What is the amplitude of 3/4 cosine of 1/2 x? And then what is the sum of that and that? These ones are easy. So what would my amplitude be on number 2? 3/4. That's true. If I said to you, I'm going to add on to that problem, what is the period? What would you say? Wrong. Oh, kindergarten. That one didn't go back to 3rd grade, I guess. Just kidding. That was, you have to remember that. What's our period, guys? It's 4 pi, because we just can't forget. No, I was just kidding about that. We forget that this is bx, and then our period is 2 pi for sine and cosine divided by b. So that's why it's 4 pi. Okay, it says, what's the sum? So we would just combine like terms and put it in standard form, right? 4x cubed, right? Minus x squared plus x plus 4? Yeah. Awesome. Okay, it says, hey, go for this one. Given f of x and g of x, find f divided by g of x. It didn't say anything about restrictions. It simply asks what's f divided by g of x.
Cool. I did it right.
Yeah.
Oh, that's negative. Yeah, my bad. What? Yeah.
We should have got this. So you factor the top. We would never do anything so tragic as to divide across addition and subtraction signs. That would be bad. But we just factor it and then divide out exact factors. So we would have x minus 2 all over x times x plus 6. And you would make sure to type it into the calculator with parentheses or distribute it through and type it in that way, yeah. Yes. X, and we would make sure to not miss up on one sign or else we'd get it wrong. Good point. I guess I have to go back to 6th grade. They would have it in their algorithm and for a stage that you could get it right for either or, because not one's more simplified than the other, as long as you use parentheses. Okay, go for it. Nope. That's how you spell triple. That is not true. Just kidding. You're right, we talked about this one other time, but if I don't spell bad, it's not in my nature. I need to fix it. It looks right to me. You know what? I didn't have to write a paper my whole degree. Because I got a math degree, so give me a break. Okay, that's not true. I did have to take generals, but once I got into math, I didn't need to write a paper. Yeah, let's do that. For all you smart people that happen to be good at math and English. Just kidding. I'm just crazy. That was rude. Really?
Yeah.
Well, I'd be off a lot of points. Okay. All right. Triple the amplitude and decrease the midline by 4. So you wrote 9. Sine, does that affect B? Good. Good. Awesome. What if it said with a phase shift of 2? Wouldn't that be your right 2? A phase shift is a shift left and right. Oh, by 4. Okay, let's just erase that. Minus 4. Okay, if I said a phase shift, that's a shift left or right, right? So that'd be, you'd have to make sure that's in your parentheses. But, all right, we're all good. Okay, last one. Find the average rate of change. Every single one of you will get an average rate of change problem. It's been a long time. You can just think about it, or you can use the formula for average rate of change, which I use every time. Average rate of change is, and every single one of you will get an average rate of change problem. So this is one you need to put a big star by to review. F of B minus F of A. So change in the functions divided by change in the x values. So F of B minus F of A all over B minus A. You will all get an average rate of change problem for sure. Yep. So this is A, this is B. A is your lowest point on your interval, B is your highest point. So what is, this is X, this is Y. So isn't this X, isn't this F of X? Everybody?
Yeah.
All right, so guys, if I know that A is -2, what's my F of -2? Isn't that F of A, everybody?
Yeah.
Which F of -2 means what's my function at -2? So my answer would be -13. If I know B is 1, my function at 1 would be F of B, which is 2. Now all you gotta do is 2 F of B minus F of A, so minus -13, all over B minus A. So 15 over 3 equals 5. The average rate of change is 5. You can think of it easier, like you can't just think about it, but if you have the formula, you can always do it too. Because sometimes they'll give you a function like that, and we'll get examples like that later. I mean, as we go through it this month, we'll do another one. What? That's the average rate of change over that interval in the function. All right, let's get going on today's lesson. So we know how to take a rectangular equation or a rectangular point and convert it to polar, and switch back and forth between polar and rectangular. Today we're going to take a rectangular complex number and we're going to switch it to the trig form of a complex number. So 9-4 is the trig form of a complex number. So we're going to talk about, once again, just a reminder, a complex number has A plus BI form. This would be the rectangular way of writing a complex number, where A is the real part and BI is the imaginary part. Let's see if I can spell imaginary. Yeah. Luckily, it's spelled exactly how it sounds. Okay. So if we were going to graph a complex number, for example, let's graph 2 plus 3i. So this would be our real axis, and this would be our imaginary axis. So we would go right 2, up 1, 2, 3. And then with imaginary numbers, they have a like direction. So we point our arrow, which is a vector. So we just graph the imaginary number 2 plus 3i. Right 2, up 3. Does everybody understand? Okay, let's graph 4i. So that would be going right 0, but up 1, 2, 3, 4 on the imaginary axis. There's our vector. Let's graph -3. So we would be going -1, 2, 3, up 0 on I, graphing that. And then graphing, once again, -1, -4i. -1, down 1, 2, 3, 4. And there's my there's my complex number graph. Everybody good? No questions? Okay. So,
Yep.
now we're going to talk about, yes?
So how do you know where this is? Like, you just go from 0?
Yeah, we just plot it from 0. Yep. Good question. We plot from the origin. So this would be all rectangular, because think about it. This is going 2 units this way, 3 units up. 2 units, 3 units up. Now, couldn't I describe how to get to there by polar type coordinates, which will then become trig, because if you think about it, so next slide here. So we're going to describe how to get to point AB by, instead of using normal old rectangular complex numbers, trig form of a complex number. So we know to get to that point, we can go up theta and out r in units, right? That's kind of polar. just the exact same thing. It's similar to converting rectangular form to rectangular form to polar form. It's very similar to convert it to trig form. So everybody, a complex number z, they just call it like, hey, this is my complex number. So they would have wrote z is equal to 2 plus 3i. They would just write it like that. Does that make sense, everybody? Z just means we have, I mean, it doesn't have to be z, but they just write, we have a complex number of this. Why? Okay. Okay, got it. So now it's going to be the same idea, guys. So think about this. This is over A up B, technically BI. So this is our imaginary axis. This was our regular old axis here. So if we go up theta and out R, think about it. So this is A, this is B. Won't A be R cosine theta, which we already know because of polar, right? And then B will be R sine theta. So let's rewrite this in trig form. So instead of an A, let's put R cosine theta. So rewriting this as R cosine theta for A plus B, which is R sine theta times I. Now we have it written as a trig form of a complex number. Now you're going to see them do something just to like make it prettier. What they're going to do is they're going to factor out an R just to write it prettier. So we factor out an R, so then left would be cosine theta plus I sine theta. That's how you're going to see them write it. Just factoring out the R. So when I do it, you're going to see me write it like this, just because that's the like prettier way of writing it. Why have the two R's when we could factor out an R? So write that down, because we're going to be using that. Okay, here's my first example here. It says, graph the complex number. So notice this is a weird complex number. It's in trig form. It's not in the complex number that we're used to seeing, A plus BI. It's in this form. It's in the trig form of a complex number. Well, we can still, we don't have to go through and do a whole lot here to graph it. We can just think about it. Theta must be pi 6, right?
Right.
Look, cosine theta, sine theta. What's our theta? What's our degree that we're going? Pi 6, everybody?
Right.
What's my radius that I'm going out? 12 units. Does everybody see it?
Yes.
So now we can very easily graph this. Go up pi 6 and out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're out here and there's my point. Yes.
What if you're,
They won't be. Good question. All right, so we just got to that point by looking at theta and R. So now let's convert it to, instead of having it as this kind of complex number, let's write it as what we're used to, the pretty complex number, the rectangular complex number. So what you do is just simplify it. We have 12 times, what's the cosine at pi 6? Do you want your unit circle close to you? Everybody, let's push pause and make sure everybody has a unit circle. Yep. Cosine at pi 6 is root 3 over 2. And then we have plus I, so we just replace that, plus I, and then sine at pi 6 is 1/2. Now we're just going to simplify it. So now it looks a lot prettier. It looks more A plus BI style without all the trig stuff. So multiply 12 in, so that'd be 6 root 3 plus 6I. Does everybody see how now it's in the A plus BI form?
Yeah.
So now it's back to rectangular. So there we go. Any questions? So we would have done that first. We would have known this was out 6 units this way and up 6I units, 6 root 3. All right, 6 root 3 units that way and up 6 units that way. Okay, let's graph this one. Same idea here. So it says, graph the complex number. It's almost easier to graph ones that are in trig form. Like really, it says go 150 degrees. That's our theta. And our radius is 3. So we would go to 150 degrees out here and out 1, 2, 3 radiuses. And that would put me at the right spot, all golden. Then from there, it says then write it as a rectangular complex number. So you just simplify it. So instead of cosine of 150, you'll say, what is the cosine at 150? Yep. So we'd have 3 times negative root 3 over 2 plus I, and then sine at 150 is 1/2. Now distribute 3 in. So we would have z is equal to negative 3 root 3 over 2, correct?
Right.
And then plus 3/2 I. It's pretty straightforward. Now it's in a plus bi form, the way we're used to seeing complex numbers. Okay, so now it says write each complex number in trig form. Notice this is a regular old rectangular complex numbers, the ones we've been seeing since secondary math 2. Let's rewrite this. Instead of getting to that point by rectangular coordinates, we want to say what would the trig form of this be? You're going to want to graph out where this lands. So you'll draw yourself out a picture. We would be going negative 2 up 2. That would put me somewhere right there. So now we're going to describe how to get there with theta and then a radius. Does everybody understand? So we are going to be using this, we're going to be using this reference angle here in a second. So we're going to need that. So let's go for it here. So if this is 2 and this is up 2, oh, this is negative 2 up 2. How do I find my radius? By using Pythagorean theorem. Negative 2 squared plus 2 squared equals my radius squared. 8. 8 equals radius squared, so my radius is root 8, which simplifies to be 2 root 2. So we'll write that in. This is 2 root 2. Now to find this theta, we can do any trig ratio, sine, cosine, or tangent. I just like to use tangent because opposite and adjacent. Everybody understanding good? Okay, so we would say tangent of theta equals 2 over negative 2. So tangent of theta equals negative 1. Is that on my unit circle? Can I find theta on my unit circle? Yes.
Yeah.
We can find tangent of theta on my unit circle. And it's got to land in the right quadrant. So what degree is this? 135 degrees. Or in radians, right? Or in radians, that's 3 pi fourths. Either or works. So now that would be good enough. So let's now put it into this form instead. We have thetas, we have our r. So z is equal to the radius, which is 2 root 2, and then parentheses cosine at 3 pi fourths. I'm going to just do it in radians because I prefer radians. And then plus I sine at 3 pi fourths, and we'd be done. Plus I sine at 3 pi fourths. That would be my answer. That's all you got to do. Okay, I'm going to show you one where tangent is not on the unit circle and what you're going to want to do. Here's my next example. Write it down. Write the complex number in trig form. Once again, a complex number we've been seeing since secondary 2. We're now going to put it in trig form. You're going to draw yourself a picture for sure. So this is over 1, 2, 3, up 1, 2, 3, 4, 5. That puts me right there. Oh, don't draw that way. Okay, we're looking at this. So now, Pythagorean theorem that bad boy, and find the radius. 3 squared plus 5 squared. 34 is what I'm seeing in my head.
Yep.
Yeah. Yep. Square root of 34 would be my radius. Then from there, we need to find this theta. So we would set up maybe tangent. I mean, we can set up any trig ratio, but tangent's pretty straightforward. Tangent opposite over adjacent 5/3. Now, if I take the inverse tangent, is it on my unit circle? No. So you could write out, I want you to actually do it in your calculator. Say tangent inverse of 5/3. Make sure it's in degree mode. Or it depends though. Like in the back of the book, if you ever see them write it as like 1.2, then it's because they put their calculator in radian mode. What'd you get? What's the decimal? But that's rounding, correct? For this, that's rounding, correct? Like this is not an exact answer. So what you're going to actually see them do is instead, they're going to go theta equals tangent inverse of 5/3. And they're going to leave it. Because that's exact. Theta is tangent inverse of 5/3. So now let's put it in. Once again, we're putting it into the trig form. So we know that Z will be equal to the radius, which is root 34, times cosine of the angle, which the angle is tangent inverse. So they'll go tangent inverse of 5/3, because they want an exact answer, plus I sine of tangent of inverse of 5/3. Just to make it exact, which is understandable. What do you mean? This is the exact same thing as actually putting a decimal, right, everybody? But this is just exact, so we're all good. You would probably do this, but you're not going to have this one on stage. It's going to be way more difficult than what they'll have. Good question. Questions on that one? So once again, that's just, we could put the decimal, but when we can be exact, let's just do that and leave it. Okay, so now we're going to talk about, we know if we wanted to multiply two complex numbers like this, 2 plus I, for example, times -3 minus 2I. We would know how to do that double distribute combined like terms, right? Right. But once we put that in, let's say we had a complex number in trig form, a complex number in trig form, those two being multiplied together. So this is what's going to happen. Think about multiplication. Can't you reorder it? So R1 times R2. And then wouldn't we be double distributing and combining like terms? And then don't we have to change all of our I squareds to -1? And then you would combine like terms again. So lots of algebra, and it's going to simplify to be this. So just write that down. If you care about where that comes from, that's great. Go back and actually multiply it out, double distribute, change your I squareds to -1, and you'll see where the formula comes from. We don't have time and cost to do it, but it's very doable. So if you had a complex number in trig form multiplied to a complex number in trig form, you'll just take and multiply the radiuses. Radius 1 times radius 2 times cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Notice it's plus in here. You add the angles. And then when we divide two complex numbers, we're going to do lots of algebra, same idea here. Now, if we had a complex number down here, to get to this, we would multiply by the conjugate, correct, everyone? Remember this? If we have 2 plus I over -3 minus 2I, isn't the only way to fix the I to multiply by the conjugate? Right. So it's just going through and doing buttloads of algebra for this one and simplifying it out, and you'll get this. So you can just divide the radiuses, R1 divided by R2 times cosine of theta 1. Now it's minus theta 2 plus, still plus right here, it's always plus on in between, and then theta 1, so I sine of theta 1 minus theta 2. Can anyone think of why up here, is there any reason why we would add, and down here why we'd subtract? Okay, you're thinking in the right direction, but it's actually a very simple answer. That's what I'm looking for. When you multiply, you add. Does that make sense? When you divide, then you subtract. So, I mean, it makes sense. That's how it helps me remember. Here we go. Ready? You have those written down? Five, 4, 3, 2, 1, and you missed it. Your 2 grams was off. Just kidding. Do I need to go back, anybody? For reals? Okay. Here we go. A complex number multiplied to a complex number. What a nightmare. To distribute and combine like terms and then change I squared and then calculate each of it. So luckily we have the formula here. We can literally just reorder this. 2 times 3 times cosine of pi thirds theta 1 plus theta 2, which is 11 pi 6. Plus I sine of pi thirds plus, oh, I couldn't read my own handwriting, 11 pi 6. All right, so what is that? 6 times cosine of, add those up in your calculator real quick so you don't have to get a common denominator, and you get 13 pi 6. Plus I sine of 13 pi 6. Now you can actually calculate. What is the cosine at 13 pi 6? Now let's think advancedly for a minute. Where is 13 pi 6? Now let's just think about it. What's 12 pi 6? Everybody, 12 pi 6 is 2 pi. So wouldn't 13 pi 6 just going up an additional pi 6? So just look at pi 6. It's a reference angle or a coterminal angle. So really we're just looking at pi 6, everyone, because that's the same thing as 13 pi 6. So then from there, we have 6 times, what's the cosine at pi 6? Root 3 over 2 plus I sine of pi over 6 is 1/2. So then we would distribute, and our final answer would be 3 root 3 plus 3i. And now look, it's a regular old a plus bi complex number, a rectangular complex number. Not too shabby. It's kind of shabby chic. Just kidding. Oh, yeah.
So would you simplify that by taking out 2?
You wouldn't need to, but you could. Yeah. Hey, let's do a division one. Here we go. R1 divided by R2. So we would do 24 divided by 6. Cosine of 150 degrees minus 30 degrees plus I sine of 150 minus 30. Everybody see how we're doing this? 4 times cosine at 120 plus I sine at 120. And then you would just calculate it. So you'd go to 120 degrees. The cosine at 120 is -1/2. So 4 times, that becomes -1/2. Plus I sine at 120 is root 3 over 2. You don't need to take notes on this one, do you? You can if you really want. And now we would just distribute. So that would become -2 plus 2i root 3. And now it's a normal complex number. If I said raise a complex number to a power, so for example, let's say I had 2 plus 3i raised to the 10th power, we could go through and do this using the triangle thing, Pascal's triangle, right? And whatnot. But there's an even easier way. If we have this in the trig form, it's actually really easy to do this. So we would put it in trig form. We would convert 2 plus 3i to the trig form of 2 plus 3i. And then we would use de Moivre's theorem. So what de Moivre's theorem does is it allows you to take a complex number in trig form, raised to any power, and you can do it very quickly. So if you have any complex number in trig form, such as r times cosine theta plus I sine theta raised to the nth power, you can simply simplify it by doing r to the nth power times cosine, the n will come down and multiply to theta, plus I sine of n times theta. So this is raised to the n, but then n is multiplied to theta right here and right here. Yes?
So wait, why is it that when you don't, isn't it kind of like
Well, the de Moivre's theorem, if we could go through and prove why this works, if we really wanted. Well, first of all, this is okay to put this to the nth power, right? Multiplication. But then what you'll see is when we go, you can look in the book too, they go through the proof process of why de Moivre's theorem works. But I just didn't want to get into it because we just didn't really have a whole lot of time. But if you go through and actually start distributing this and see what happens, it actually works out to be this. It simplifies to be this. So this isn't theta to the nth power though. So it's not breaking the forbidden rule. It's different. Does that make sense? Yeah. If we were to have this to the nth power and this to the nth power, that would have been breaking the forbidden rule. Does that make sense, kind of? So you could get into, if you're curious on a proof of de Moivre's theorem, search it on the internet and watch it. There's a lot of people that have gone out there and do it. So de Moivre is a mathematician that figured out that it always works out this way and came up with a proof for it mathematically of why. Did you write it down? Okay, here we go. So we have, luckily, which seems weird because you're like, it feels like it might be harder, but it's actually easier. We have the trig form of a complex number, and it's raised to the third power. So lucky for us, we don't have to multiply this out 3 times. We can just use the Morse theorem. So that'll be 2 to the third power times cosine of 3 pi fourths times 3 plus I sine of 3 pi fourths times 3. So that's really 8 times cosine at 9 pi fourths plus I sine at 9 pi fourths. And now you'll just actually evaluate it. So think about where 8 pi fourths is. 2 pi. So we'll go up another pi fourths, put us at 9 pi fourths. So we should know this one right off without even looking at our unit circle. This is 8 times root 2 over 2 plus I. Very good. Now we would distribute 8 through. 4 root 2 plus 4I root 2. Or 4 root 2I. Right, multiplication doesn't matter. So I kind of wrote that word. No, actually, I think that's how, I wrote it like that because it felt natural because of like, that's how you see the quadratic formula written and stuff. It just felt natural. So, yeah. Yeah, I think it is. Okay. Did everybody see how that was actually really quite easy? Okay. So looking at this one, how many of you would like to write this out 5 times, double distribute, then have to go back, combine all of your i's to make them, any I squareds have to be -1, that would be a nightmare. In fact, you could do it, it'd probably take you 45 minutes to an hour to get the problem right. Oh, yes. Yeah, that would be, yeah. So luckily, we can change this to the trig form. No, but you can get a pat on the back. Okay. So let's go ahead and convert this to the trig form because that's going to be much easier because then we can use the Morse theorem. So here we go. Remember, to convert this, ignore the 5 for a minute. We're just going back to what we learned at the very first of the lesson, converting this to the trig form. So you'll draw a picture. That's going, if we were graphing this, we'd be going right a half, right? Down 3 halves. So we're drawing a right triangle. So right 1/2 and then down -3. What? Okay. Jared, stop. Then we would Pythagorean theorem that bad boy to figure out that we want theta and the radius, correct? So we would Pythagorean theorem, and interestingly enough, our radius comes out to be 1. And then we can figure out theta by setting up any trig ratio. So I'm just going to say tangent of theta equals opposite over adjacent, that over that, which is -√3 over 2 divided by 1/2, so times by 2 over 1. So isn't that -√3?
Yes.
Doesn't that happen at, where does that happen on your unit circle? At negative, well, we could say it 2 different ways. 300 degrees. Doesn't it happen at 300 degrees?
Yep.
So our theta is 300 degrees. So theta equals 300 degrees. Perfect. So now we can convert it. We would have our radius, which is 1 times cosine at 300 degrees plus I sine at 300 degrees. And then that's raised to the 5th power. And now you say, okay, it looks like we made our life harder, but the Morse theorem makes it easier. So now we'll do 1 to the 5th power, then 5 multiplies in here and here. So we'll have cosine of 1500 degrees plus I sine at 1500 degrees. Now we're going to want exact answers only. So where is 1500 degrees on my unit circle? So wouldn't we take 1500, subtract 360, subtract 360, subtract 360 until we get to a place on a unit circle? Okay. Find what's coterminal. Yeah. You're right, it's 60. So same thing as 60 degrees. Same thing as 60 degrees. So then we have 1 times the cosine at 60 degrees is 1/2. And then the sine at 60 degrees is root 3 over 2. So we have plus I root 3 over 2. Now we'll multiply 1 in. So obviously our answer is just 1/2 plus I root 3 over 2. Who would have seen that coming? Not me. Multiplying that bad boy out, back up at the top. Is everybody get that answer written down? Multiplying that out, I didn't see such a small change in my answer happening. Kind of interesting. Yeah, it looks pretty close, huh? I mean, it is pretty much the same. Okay, awesome. That's it. It looks like more than it is. It's really not, because it's only every other odds right here. Yeah, there's not very many. 1 through 23 odds, 33 through 57 every other odd. 59 to for what?
You know, like, oh, we have tomorrow.